Hello everyone, welcome to my channel again. So in our previous video, we already talked about how we can do the linear regression and how we can use the hypothesis test to check if these two variables x and y has a linear relationship or not. So in this video, we will continue on our linear regression and we will move to the estimator of our parameter beta or 0 and beta 1. So now we work on the confidence interval of our parameters. So of course, here similar to our previous videos, we still denoted our linear regression line as the equation y equal beta 0 plus beta 1x plus epsilon. So here for the epsilon, the error term, we still have the assumption this epsilon follows a normal distribution with mean as 0 and the variance as sigma. So here in our previous video, we already said here for our beta 1, we can have an estimator of our beta 1 denoted by beta 1 hat. It also follows a normal distribution, and here the mean is a true value of our beta 1, and then the variance is sigma square divided by s sub double x. So here s sub double x is a value we can compute from our data set. So here I write down the equation for this one. It's equal the sum from 1 to the last data as the square of our data of x and minus the number n, which is how many pairs of the data we have, times the square of the sample mean of our x. So because our estimator of our beta 1 follows this normal distribution, then by our knowledge of the confidence interval in our previous video, we already know if we given a confidence level alpha, then we can write this based on the table of our normal distribution. We can write this confidence interval for our beta 1. However, this is only true when we know the true value of our sigma. So here sigma is the variance of our error term, right? But in generally, we don't know this. So what we can do is we can use the estimator of our variance sigma hat to replace the sigma in our function. And this also means instead of use a standard normal distribution, here we should use a t-table. So I write down the conclusion here. And if you want the more information about how we can get this one, so please look at my previous video about the confidence interval. So for 101 months alpha percentage this confidence level, so we can have the confidence interval of our beta 1 is the beta 1 hat minus the t alpha over 2 comma and minus 2 square root of sigma square hat divided by s double x. So this is a left endpoint, and then we change the minus sign to a plus sign. So this is our right endpoint. And here for each of the here we should careful about our t distribution. So please remember, because this is about confidence interval, right? So that's why we should use a t sub alpha over 2. And then also for this one, here we use n minus 2 as our degree of freedom. So this is very similar for our previous video about the hypothesis test in our linear regression. So this is a formula how we can compute for our confidence interval. And then please remember here the term we use it to minus and plus to get our left endpoint and right endpoint of our confidence interval. So here about the term t sub alpha over 2 comma n minus 2 and times the square root of our variance for the distribution of our beta 1 hat. So this is our ME. So this is our margin of error. So we denote this as ME. So here if the question asks you what is ME for one of the estimator of our beta 1, then we should know this is the term about our t times this square root. Okay, so this is about the formula we have. And now let's we work on an example to see how we can use this formula to compute the confidence interval or ME. So here the question is find a 95% confidence interval for our beta 1. When we have the estimator of our beta 1 is equal negative 0.59, the estimator of our error variance is 0.72, the S sub double X is equal 32.8, and the number of our data set is equal 5. So this example, we also mentioned this one in our previous video when we talk about the hypothesis test. So if you haven't know what is a hypothesis test to check about linear regression between two variables, you can look at my previous video. So now if we want to compute this confidence interval, the first thing we should compute is we can compute about the ME, and after we get the ME, then we can use this ME to compute the left and right endpoint. So here, what is our ME? ME is T sub, so here our ME is our T sub alpha over 2, comma n minus 2 times the square root of our sigma hat square divided by S double X. So to compute this one, the first thing is we should know what is our T alpha over 2. So because here the question is ask us about the 95% confidence interval. So that means we have the alpha is equal 1 minus this 95%. So in other words, it means alpha is equal 0.05. And then for this one, this means we can plug in alpha equal 0.05. So this is 0.05 divided by 2. And for our n is equal 5. So here, by the formula, we have this is a 5 minus 2. Okay, so this is all about our t term. And then about the square root, we just plug in our value about these two numerator and denominator. So the numerator is 0.72 and the denominator is 32.8. So this is about the equation we need. And then now what we need is we can use the calculator and we use the table of our t table. So we need to find the value of t sub 0.025, 3 and also use the calculator to compute this square root. So by the calculator and the half of the t table, we will get for the first term, this is equal, t term is equal 3.182. And then, because this one is equal, the t term is equal this one, so we will get, by calculator, the final answer of this one is 0.47. So this is our margin of error. And because we have this margin of error, so that means we will have our confidence interval. So our confidence interval will have the left term is our beta hat 1 minus our ME, and the right endpoint is beta hat 1 plus our ME. So because in the question, they already give us the estimator of our ME, of our beta 1, and we also compute the ME. So here what we have is we just plug in the answer. So for the left endpoint is negative 0.49 and minus ME, so minus 0.47. And the right endpoint is for the plus. So we have the similar equation, but just plus over ME. So here, this is about the plugging the value into our formula. So then the next thing is just use a calculator, right, to get the answer. So for the left endpoint is negative 0.96. And for the right endpoint is negative 0.02. So this is our equation for the confidence interval. So if we look at this confidence interval for our estimator of beta 1, so we can find, in fact, both of the left endpoint and right endpoint are both negative value. So what this means? This means 0 is not in the confidence interval for our estimator of beta 1. So here in our previous video, we talked about when we try to do the hypothesis test about the linear relationship between x and y. We always say if beta 1, the estimator is equal, the true value is equal 0, then that means we will reject this claim. So that means x, y cannot say they have a linear relationship. And in other words, if now we look at this 95 confidence interval, we find 0 is not inside this confidence interval. So in other words, because this 0 is not contained in our confidence interval, we can reject a claim, a non-hypothesis, the H0 beta 1 is equal 0. So this is a remark for our video, and we can also say this is help us to know what's the relationship between a confidence interval of beta 1 and a hypothesis test of beta 1. Okay, so this is about this example. And next, before we talk about another type of the confidence interval here, let us talk about why people do the linear regression here. So, of course, when we do a linear regression, the main idea is we need to decide or estimate the value of our beta 1 and beta 2. So, in other words, we want to construct a linear regression line, the y equal beta 0 plus beta 1x by our data set, right? So then why we want to construct this equation or line, or in other words, how we can use our result about this line. So the first one is in the real world, like, data set is a kind of a sample, right? It's just give a sample, and we always use the information of the sample to try to get the information of the population. So here, if we use this regression line to get a relationship between our y and x, then in future, if we know some information of our x, then we can get the underlying distribution in terms of our x. So this is one we can do for you can see the application of this regression line. And also there is another one which is also very popular. So this is in case like now if instead of our original data set, now we have some more data, and this data is about our x. And by this new information of x and this regression line, now we can get the information of our y. So in other words, it's like we can predict some y's value, and if we get new information about our x. So this one is sometimes in statistics and engineering, this is more popular. So now, like when we have some original information about our x and y, we use this information to get a relationship, and this construct our this regression line. And then in the future, if we want to know some new information about y, we can just work on the x, and when we get new information of x, we can use this one to predict the y. So that means here, of course, in general, it means x is a cheaper data. So in other words, if we want to take a survey, then it's easier for us to get the information of x. And the y is a more expensive one. So it's hard for us to get the directly information about y. Okay, so this is about the application of our regression line. And then when we have a new value of our x, then we have a name for our computed y value. So let me write down the name here. So here, when we fix our value of x is equal denoted by x0, then we can use our construct the regression line, the y equal x0 hat plus beta 1 hat x, the estimator of our beta 0 and beta 1. So by plugging this x into our equation, we can get a response of the expected y value here. And then we denoted this one as an equation like the mu hat y given x0, or in other form we have the mean, the e parenthesis y given x0. So here, please remember this one is not a constant number, because for our estimator of beta 0 and beta 1, we can have different value of the estimator, right? If we change our original data set, we can get different estimator of our beta 0 and beta 1. So here, based on this one, so now what we want to do, we want to find the confidence interval of this mean of our response. So this is our next topic about the confidence interval in our linear regression. So to find this confidence interval, let us recall what we do before in the start of this video about the beta 1 hat. So when we try to find the confidence interval of our beta 1, the first thing is we talk about the distribution of the estimator of beta 1, right? We said because beta 1 hat, the estimator of beta 1, follows a normal distribution with the mean as beta 1, and the variance is sigma squared divided by s double x. And then the next step is so smooth. We just say, okay, because we don't know the true value of sigma, so we use the sigma hat to substitute it. And then everything will follow a t distribution, and we get the confidence interval by get the ME, the margin of error. So here in this part, what we should do, the first thing is we should still get what is our distribution of this mean response, our mu hat sub y given x0. So the first thing is, here I will skip about the process about how we can compute this mean of this one. But if you're interested one, just leave a comment. Maybe later or in the future, I will post a video about how to compute this one. So here, the lucky thing is, if we compute the mean of our mean of response, we will get this one is equal. It's just equal its true value. So in other words, it means this estimator of our mu y sub y given x0 is a unbiased estimator. So let me write down this as a remark. Okay, so now we get the mean of our mu hat. And then the next thing is we still need to find the variance here, right? So here about this variance, of course, again, I will skip about this computation part. And if you're interested, just leave a comment. So here, let me write down, directly give you the answer. The variance of this one is also related to our variance of the error term. So this is sigma squared times 1 over n, and plus the second term is x0 minus the sample mean of our x, take a square and then divided by again as sub double x. Okay, so this is about the variance of our mu hat. And then this is only the mean and variance, but we didn't say what is the distribution of our mu hat. So now this one is about how we can know the property of the normal distribution. So in our previous video, when we talk about the property of linear regression, we said beta 0 and beta 1 estimator, both of them follows a normal distribution. So here, because our mu hat is a linear function of our beta 0 and beta 1, right? Because it's equal beta 0 hat plus beta 1 hat times x. So that's why here we have, by the property of normal distribution and the linear function, we know for our mu hat is also a normal distribution. And also because previous we already compute the mean and variance here. So that's why here for our mu hat and y sub y given x 0. So here we can write this as our true value of our mu, and also about this complicated equation for our variance. Okay, so now we have about this is the distribution of our mu hat. And then similarly to our previous part at the start of this video, the next thing is if you look at this value of our variance, right? This is the variance of our error term. Of course, if we know this true value, what we can do, we can just use the standard normal distribution table to help us find the confidence interval. However, in generally, we don't know this true value of error term. So what we can do is we use the estimator of our variance to replace this sigma square. And then in this case, this will follow a t distribution. So in other words, now we can have this equation, this statistic have. So this equation, we minus the mean of our normal distribution and divided by the standard error of our normal distribution. And also we substitute the sigma hat, sigma square by sigma hat square. So we know this one follows a t distribution. And please remember again, here the degree of freedom for our t distribution is n minus 2. So now by this one, we can give our final conclusion about our confidence interval. So for given alpha, we will have the confidence interval is for 100 times 1 minus alpha percentage. The confidence interval is as this equation. So here again about the term after our plus or minus. So this is our ME, the margin of error. And then here if we have the estimator of our mu y given x0 minus the ME, this is our left endpoint of confidence interval. And if we plus ME, so this is right endpoint for our confidence interval. And so here again, because we work for confidence interval, right? So we still use T sub alpha over 2. So this is very similar for our previous confidence interval for beta 1. So now this is about how we can compute a confidence interval for our mean response. And then let me again give one example about how we can use this one. So the example about this question is a continuous example for our previous question. So that means here we still have the similar setting up. So we still have the similar value for our, here the beta 1 hat is equal negative 0.49 and the estimator of our sigma square is equal 0.72. We still have the 5 data in our data set, and we still have the S sub double X is equal 32.8. But because this one is work for the mu, the mean of response, so we still need 2 more value. One is about the estimator of beta 0. So here this is equal 4.05. And also we need the sample mean of our x, so it's equal 4.2. So now the question asks us what is the 95% confidence interval of our mu when or at our x0 is equal 3. Okay? So here about this question, the idea of the steps is very similar for our previous example. So here the first one is we still want to find what is our ME. So here because our ME, we have this equation is equal T sub alpha over 2 comma n minus 2. And then this square root is still about the variance or the standard, like square root of variance or our standard error. So here for this one, the only difference is for our mu, this is a little more complicated than our beta. So here we have this equation, it look like this. And now the step when we have this formula, what we need to do is we need to plug in our values here. So again, similar to the previous question, because we have the 95% here, so that means we have the alpha is equal 1 minus 95%. So alpha is equal 0.05. And so here, when we plug in 0.05 to our alpha over 2, we will have this is equal 0.025. And again here for our n, because n is equal 5, right? So what we have is 5 minus 2, so we have this is equal 3. And then the other thing is we need to plug in all of the value here. So the first about sigma hat is equal 0.72, and then inside this parenthesis we should plug in all of the value here. So after we plug in all of the value here, the next step is we should just use our calculator to help us compute this equation. And also we need the t-table to help us find the value of our t sub 0.025, 3. So this value of t is same with our previous question. So it's still 3.182. And then we get the compute of our calculator of the square root. So that means here the final answer of this one by calculator, we will get this is equal 1.33. Okay, so this is our ME. And because we have this ME, so next thing is we just get our estimator of mu plus and minus our ME. So here what we have is for the left in the point, when we plug in of the O value here, we will get the equation is as this one. And then we can have this left in the point and right in the point as 1.25 and 3.91. So now we can have our conclusion. The 95 percentage of our mu hat y given x0 at x0 equals 3 is interval as 1.25 and 3.91. Okay, so this is about how we can do the confidence interval to find the value of the estimation for our beta 1, and also about the mean response. So in our next video, we will talk more about how we can use our regression line to predict the new value of our y. And so please subscribe my channel and see you in the next video.